In this video, we're going to explore some examples of functions for which the limit doesn't exist when x approaches a certain point. In the previous video, we saw an example of this case when we had that the one-sided limits were different, so it was impossible for our function to get very close to a single value. In this video, we're going to see some other examples where, again, the limit doesn't exist. What is the idea of that? Well, first of all, what is the idea of the limit exists? Well, the limit exists if there is a real number such that the limit as x approaches c of f of x is equal to L, right? That's what it means that it exists, is that it is a real number. So, if we want to expand these and express it in words, we say that the limit exists if we can make the values of f of x to be very close to a number L, provided that x is sufficiently close to c. And then, well, if I want to say that the limit as x approaches c of f of x does not exist, well, that would mean that it's impossible to find a real number such that the values of f of x get very close to that value for x sufficiently close to c. As we saw with the example of the two one-sided limits being different, it was impossible for the values of my function to be very close to a single value for values of x that are very close to, in that case, was 0. Okay, so that is the idea of the limit doesn't exist. So how can we then look at examples? The first one I want to take a look at is a very weird function in a way. It's this function given by sine of pi over x. The first thing to notice here is that f of 0 is not defined, right? There is no way I can plug in 0 there because we have x in the denominator. Okay, that's problem number one. Now let's study what happens for that function at some values of x and see if we can make a guess of what the limit should be or if it exists. Well, let's see. F of 1 over n would be sine of n times pi, and we know that if we have an integer multiple of pi, then sine is 0. So we know that f of 1 over n is equal to 0 for all n in the natural numbers. Now, it is very tempting to guess then that the limit as x approaches 0 of sine of 1 over x, of pi over x, is equal to 0. It sounds plausible, but our guess would be completely wrong. You will see soon how wrong this guess would be. You see, if I take f of 2 over 4n plus 1, that would be sine of 4n plus 1 times pi over 2. So, for example, if n is equal to 1, that is 5 pi over 2. If n is equal to 2, that is 9 pi over 2. So if you look at the unit circle, we're always going to be at the very top of the circle. So this is 1. For any natural number, this is 1. So we have numbers that are as close to 0 as we like them to be. We can do that using, for example, the Archimedean property. 1 over n is as close to 0 as I want to be, provided that n is large enough. And f of that number would be 0. But again, if we take n very large, f of 2 over 4n plus 1 would be 1. So it is impossible that we're really approaching a single value. And if we plot the graph of this function, it behaves quite widely. When we're getting very close to 0, our function sine of pi over x becomes like oscillating very rapidly, goes up and down like crazy, taking all the values between -1 and 1 infinitely many times. So it is absolutely impossible for our function to stay close to a single value when x is very close to 0. And that is why the limit of this function as x approaches 0 doesn't exist. It's not just because the function was not defined at 0. We know that that is not really a problem. The problem here is the behavior of the function close to 0. We know that when x is very close to 0, my function becomes extremely wild and begins to oscillate up and down between -1 and 1 without any chance of settling around a particular value. Okay, now we know that the limit as x approaches 0 of sine of pi over x does not exist. Very often you will see me writing dne. When referring to a limit, that would mean that it does not exist, just to make it a bit short. Now we want to consider a different example, and again, the limit is not going to exist, but it's not going to exist in a different way. We're going to take a look at the function 1 over the absolute value of x minus 2. F is not defined at 2, so f of 2 is not defined. That we know that that's not a big problem. We've already computed limits that existed when the function was not defined at the point where x wanted to tend to. And here we have a graph of the function. And this graph really highlights the real problem with this function. And is that if you look at it, when x gets very close to 2, then the values of f of x become arbitrarily large. They tend to infinity. So what we're saying here is for x very close to 2, f of x becomes arbitrarily large, and therefore it is impossible for the function to stay very close to a single real number L. So again, the limit as x approaches 2 of 1 over the absolute value of x minus 2 does not exist. However, this limit doesn't exist in a very special way, because we can say a lot about the behavior, right? We're saying that the values of f of x become arbitrarily large. I can make them as large as I want, provided that my x is close enough to 2. So this, in a similar way to what we discussed when we talk about limits for sequences, we will say that the limit as x approaches to 2 of 1 over the absolute value of x minus 2 is infinity. Just to capture the behavior that the values of my function get arbitrarily large when I get extremely close to 2.